Hello. In this video I want to introduce the important tool that is called support functions. Now support functions are more general. It's not just for random sets. It's something that can be used for convex analysis. If you open chapter 13 in Rockefeller's book, you can see a whole chapter on support functions. But we want to bring this tool into the random set theory. So let X be a random set, okay, on probability space omega phi f p, okay, with almost sure convex values. Okay, so X of omega almost surely is a convex set in RD. Okay, so that's okay, convex values in RD. So that's going to be closed and convex set in RD. Okay. Now let's define the following support functions. So definition. Okay. For a random set, okay, with almost sure convex values in RD, okay, let U be a certain vector in RD, okay. Okay, and let age of X U be equal to the supremum over all values X in capital X, okay, of the inner product X U. Okay, so that's the support function. Now let's give a graphical illustration of this definition. Okay, I'm going to use R2. Okay, I'm not going to attempt making a diagram in R7. Okay, so suppose at a certain value of omega. Okay, so this will be for every omega. Okay, so at a certain value of omega, let's say we have X of omega. Okay. X or X of omega is this ovalic shaped set which is convex. And also let's say that we have a certain direction vector u in R2 in this case. Okay, so let's say it's this vector. Okay, this is u. So this supremum says go in this direction and see how far can you go until you leave the set X omega. So in this case, okay, we can only go up to, okay, we can extend this line imaginary. Okay, let's do that. Okay, here we have left the set X. So the support is going to be the tangent at this point. Okay, that's as far as we can go in this direction. Okay, that's supposed to tangent in this point. Okay, and age of X U. Okay, let's write the parallel here. Okay, so these two lines are hopefully look somewhat parallel. Okay, age of X U in this direction is going to be the distance between these two lines. Let's extend them a little bit so we can write down. Okay, and then we'll say the distance or the distance between, or the length of the distance between them. This is age of X evaluated at omega in a direction u. Okay, so you can imagine, or you can think about us rotating u in many directions, okay? And each direction we see how far can we go, and we reach that point, okay? And we measure the distance of how far we could go in that direction, and we do that in all 360 degrees in the R2 case directions. And we will basically draw the set. Okay, so if this set is indeed convex, okay, there will be only one point in which this tangent will hit the set. Okay, there are no straight or kinks. Okay, so there can be straight faces, that's fine, but there are no kinks in which you could choose any. Okay, so there is no something that looks like this. Okay, so if the set would look like this. Okay, if we chose this direction, we could have a lot of tangents here, and so it's not unique. Okay, and I can still find the supermoon, but that's not going to give me a picture of the set. Okay, so if the set is convex, I can draw, so to speak, the convex set using the support function. Okay, so why is that important? Why is that useful? Well, the next videos and this video and the next videos will add some results here. But first of all, one has to say that if X is a convex set, this is a random function, okay, of U. Okay, so let's fix X to be a certain random set. Okay, so let X be convex valued random set. Okay, then this is okay. Let's say it's defined from the unit sphere. Okay, we don't really need the U to extend more than the B unit. I didn't write it here, but U can just be of unit length. Okay, so this is from the unit ball. Let's call it B1 of RD. Okay, defined to R. Okay, this is a random function. Okay, R-valued random function. Okay, and so that gives us a nice way to characterize a convex set and work with a random function rather than a random set. Okay, the importance of that will again be clear later on, because we can use some convergence results and some other results on random functions that already been proven and will be true, therefore, for the random set with convex values. Okay, another thing that it should remind you that this dealing with convexity is the Aumann expectation gives you a convex set. Okay, so if we could exploit something in that sense, that the convexity of the Aumann expectation, and maybe say something about characterizing this set in some way, that will be helpful. So this support function is a helpful tool for that reason. Thank you.